everyone. In this video, I'm going to show you how to solve for problem 6 in homework 7. Okay, this is a reversed consolidation problem process. Okay, so let's just you just need to play around with the two charts we're talking about in class. So let's take a look. So it says a large granular free draining fill 6 inch thick is going to placed on the clay, and it says a piezometer was installed at the midpoint of the clay layer. Okay, so say a piezometer is placed at here in the middle, and the water table at the original groundwater surface, the water table is at here, right? And 3 years after, the piezometer read 7.63 above the groundwater table. So that means 3 years later, piezometer gonna read Okay, so that means 3 years later, it reads above, so that's 7.63 feet above the original groundwater table. So 3 years later, the total height of the water in the piezometer gives you the pressure head at midpoint, right? And we know that it gives you the pressure, right? So give you the pressure means that before the fill was placed, your pressure head is going to be at here, right? It's going to be at the same height as the groundwater table, right? And when the fill is placed, then you're going to have excess pore water pressure. So all that means after 3 years, or at 3 years, at the third year, your excess pore water pressure head is 7.63. So it just gives you the UEZ. So this Z is actually at the midpoint, right, at the mid depth. So UEZ at mid depth gonna be 7.63 feet times 62.4, right? So the water unit weight that equals 476 psf. Okay, now what is the initial excess pore water pressure? So right after the fill is placed, all the load is taken by water. So the initial excess pore water pressure equals to the load increment equals 130 times the height of the fill, 6 feet, equals 780 psf. Right, that makes sense, right? So initially, right after the fill is placed, excess initial excess pore water pressure equals 70-80, and as you wait longer, pore water pressure dissipates, right? So like 3 years later, excess pore water pressure is reduced to 476. Okay. Then that time, and from there we can calculate the consolidation ratio. So UZ equals UEZ to UE nut ratio, right? So it's equals to 1 minus 476 over 780 equals 0.39. Okay, and it asks for what the percent of the total consolidation. So it's asked for, actually ask for percentage. So ask for U. So in order to get U, we need time factor, right? So look at what we have so far, and if we look at the chart, right? So if you look at the chart, you will see that if we, for sure we can calculate the Z, right? So it's at the midpoint. So Z is just equal to, let's figure out it's not one way or two way. It seems it's a two-way drainage, right? Two-way drainage. So my Z would be 1. So it's a two-way drainage. So at the mid depth, Z is equal to 1. And we just figure out UZ, and UZ is 0.39. So I guess we can, if we enter Z, so it's right in the middle, and then enter Z 0.3, so close to 0.4, so right here. And then we actually can figure out the time factor, right? We can figure out the time factor. Okay. Okay, so it seems that the horizontal line and the vertical line interact at here, so at the peak, right? So then from there, so first of all is at the midpoint. So when Z equals to 1, our point is right at the middle. So it should be at the peak of the curve, right? So it's right at here. So this is the curve. This is the curve representing our case. So from there, I can figure out my T sub V equals 0.3. Okay, and T is related. T is also related to time. And then if we look at this one, this curve, if we enter T sub V 0.3, and then I can get the corresponding U. Right, so U is say about 62%. So from there, so enter TV equals 0.3. Then I'll get U equals approximately 62%. Right, so that is the answer to part A. Right? Okay, now and then let's write it here. So from there, I think from the chart, UZ chart, we get TV equals to 0.39, and from the TVU chart, and we obtain that U is equal to 62%. Right, so that's answer for part A. Okay, and part B, what percent of the total consolidation of the entire layer will have occurred 8 years later? 8 years later. So it's another question of time, right? 8 years later means we need to know what is the TV for 8 years later, and from part A. So from part A, let's see, let's write it here. So I already get T sub V, right? And then T sub V equals C sub V times T over HDR squared. So that means if I enter TV and the time t, I can solve for the constant C sub V. So C sub V equals TV times HDR squared over T. Right, so it's equals TV 0.39 and forfeit HDR, oh sorry, HDR 2A, so HDR is 7.5, right, half of the thickness, 7.5 squared, and it's 3 years, right, 3 years, so divided by 3 years. Okay, and equals 5.625 feet squared per year. Okay, C sub V is the constant, right? So, and then I can reuse this equation to get the TV for 8 years, and then go back, look at the chart and find out the percent of the consolidation. Right, so, and 8 years, at 8 years, my TV gonna be equal to CV times T and HDR squared equals, okay, so C sub V equals 5, we just calculated 5.625 feet squared per year, right? And 8 year HDR still 7.5 feet squared, right? And I got point A, right? And then what I'm gonna do is find the right chart. So enter point A. So enter point A and read my U. So it's about a little bit less than 90%. So I'll say perhaps 89%. Read the U TV chart. U is about 89%. Okay, so that answers the question. Okay. Okay, and then part C asks for what is the effective stress at the 3-year at the Z equals 5 feet. So what is Z? Is 5 feet. Okay, can go back. Okay, what is the effective stress at the depth of 5 feet in the clay 3 years later? Right? Okay. Okay. Then the first thought is I can get the depth ratio, right? So depth ratio is Z over HDR, and I can, and then I can easily calculate it, and that's equals 0.67, right? And at the 3 years, and we figure out my TV time factor is 0.3, right? We calculate from the previous steps. So first thought is from that I can get my UZ. I can get UZ from the chart, right? So if I enter TV is 0.3 and the Z is 0.67, so it's about 0.5, 0.5, and then so in the middle 1, 2, 3, 4, 5. So right here is about 0.75. So 0.75. So somewhere around here. So we are looking for 0.67. So here is 0.65. So a little bit below that, so we come over here, so probably here. So if we draw a line down, so located here, so it's approximately about UZ equals 0.48, right? Okay, you can read from 0.48. What that means, well, let's rewrite the expression of UZ. UZ equals 1 minus UEZ over UE nut. Okay, and then asking for the effective stress. So now we use a different method. So of course you can solve for UEZ and then solve for the actual pore pressure and solve for the actual total stress and find the difference between the total stress and the pore pressure. Now let's look at the other way. Okay, let's rewrite it is equals to the UE nut minus UEZ over UE nut, right? And so the numerator is the loss of excess pore water pressure. So that loss will be added to effective stress. So the loss of excess pore water pressure equals to the increase in effective stress. So that means I can calculate my effective stress increment. So equals to UEZ times initial pore water pressure, right? So okay, you write it out. So equals UZ times UE nut. So UZ is 0.48 and UE nut is the load increment caused by the fill. So it's gonna be 780 PSF. 780, right? So what is coming from is 130 times 6, right? 130 times 6 is the UE nut, and equals 374.4 PSF. Okay, so that's the increase in effective stress. Now, initial effective stress at the mid depths, at the depths of 5 feet, right here. So that's the effective stress right before the fill was placed. So it's equal to 102.4 minus 62.4 times 5 feet. Right. So equals 200. Simple enough. Okay. So that is the initial effective stress at 5 feet right before the fill is placed, and after the fill is placed, and after 3 years, the effective stress is going to be increased to 200 plus 374.4 equals 574.4 PSF. Okay. So that's maybe an easier way to do it. Alright, I hope this video can help you with a better understanding of this concept, and thank you for watching.